So the first thing is we looked at different kinds of powders in the last class. In trying to look at different types of processes that we will do tomorrow, dye compaction, which is just with powders with solid lubricants, right? So there is no solution processing or melt processing. In injection molding, you need the polymer to be a melt. So you heat it up, it goes from the solid state to the liquid state, and then you process that. Right? In the case of slip casting and tape casting, you dissolve the polymer in a solvent, right? And so the properties of what solvent dissolves which polymer, and so the interactions between the solvent and the polymer become important at that point. And also how, depending upon the concentration and molecular weight of the polymer, how that changes the properties of the solution in terms of the flow properties, the rheology. And then once you add powders, how the flow properties change, because you need to create a shape. So slip casting and tape casting is with solutions of polymers. Injection molding and extrusion is with polymer melts. And dye compaction is an example where the additives are used in the solid form without any liquid phase present. Right? So given that there are so many different powders, so many different processes, and so many different shapes for different applications, how do you select additives? How do you modify additives such that they work in all these different situations? Is the big challenge. Right? We saw in the last class that powders can be of all different varieties. Right? And so how do you change the selection of the additives to suit the process, to suit the powder, to suit the geometry? Right? They are interrelated. How to understand a logic to go with being able to make this all work out. I mean, take your zirconia particles, for instance. Right? You need them to be de-agglomerated. That is, the agglomerate should be a breakdown and it should disperse evenly. What might work for making a homogeneous suspension in water for zirconia might be different from if for the same zirconia you use a different particle size, or with the same particle size you go from an aqueous medium to a polymer melt, right? So how do you disperse it in the two different cases become quite different, and the properties of the mixtures become different. Because if you wanted to make zirconia by dye compaction or injection molding or tape casting, there are three different limiting cases of what you mix with it, right? So we need to understand polymers in the context of how they interact with powders, right? And so that is why the nature of this field becomes more specialized compared to just pure polymer chemistry or organic chemistry, because the interaction with the surfaces and the powders changes the properties, changes the applications. So polymers, small molecules, right? Those are the two different variations. So solvent is an example of a small molecule, low molecular weight. Polymer is a very high molecular weight material. And because of the difference in molecular weight and the chemical architecture, the properties between a small molecule and for a large polymer are going to be quite different. And being able to understand the difference because of the difference in molecular weight becomes important. Right? And those are the terms that you end up seeing in the case of chemistry. When you come to processing, you come across all these different kinds of terms. Binder, right? What's a binder? Something that holds things together, something that bonds things together. It came from the paint industry. So some polymers are called binders. Once you create a shape, it holds the powder and the shape together in an intact manner. Right? Lubricants. So in some cases, you had to push the powder into a die. There is a lot of friction. Right? If it's ceramic particles, they're very hard and abrasive, and a lot of the energy that is used for compaction is dissipated by powder-powder friction. Also, if you have a die cavity to make a shape, what happens is the die itself will get abraded by the motion of the powder against the wall. So you need some lubricants to be able to reduce the wear and to reduce the friction between the powder and powder surface so that particles can slide across more easily. The more easily they can slide past each other, the higher the density of the part at any given pressure. Right? In the last class, we looked at different types of densities. You remember? Can you give some examples of what kinds of densities we looked at? Apparent density, good. What is apparent density? Yes, so just what is called bulk density in common parlance. If you didn't apply any agitation, how much, what is the packing characteristic of the powder, right? So what is another type of density? So this is a what we are referring to as a compaction density, right? Compacted density. You apply pressure and you can push the powders closer together, right? The higher the pressure, the higher the density, but there is a limit, right? Beyond a particular limit, you cannot push the powders any closer together. And it depends upon the mechanical properties of the powder themselves. If it's a soft metal, it might compact a lot better at a given pressure. If it's a hard particle like a silica or a zirconium, it's going to be compacted to a lesser extent. What we are trying to do with the lubricant is to make sure that for at lower pressures you can compact it in a more uniform manner. In doing so, you're consuming lesser energy. There is less wear on the die itself. And so, from a manufacturing perspective, defects generation as well as cost for manufacturing, two things that we talked about in the first lecture as some things that we would like to do, right, can get affected by that. Okay. Surfactants and dispersants are sort of related um, to each other. In both cases, they cover the surface of the particle. Okay. In one case, the surfactant helps to increase the compatibility, so the bond between the powder surface and the polymer surface. Okay, so that's when you refer to surfactants, that's what we look at. When we talk about dispersants, we are also talking about polymers or some kinds of surface adsorption of organic molecules. The main difference is that you want to separate powder particles from each other. Okay. You are not so worried about the strength of how the polymer sticks to the surface of the powder. You are more interested in making sure that the powders don't stick to each other. Okay. And so the nature of the chemistry changes a little bit. And then finally, solvents. You can dissolve some of these things in a solvent and you can disperse the particles on that. And so you might see that in your at the output of your Stover process after synthesis. You have it as a suspension or you can have it as a dry powder. Same thing after the zirconia nanoparticles. For you, you're doing a gas phase synthesis or you're doing electrochemical anodization of films? Is that what's okay? Okay. What temperatures are you doing that at? Okay. And you're building it on a foil or an evaporated film?
on a foil,
Okay.
thin film.
Okay, fine. Okay. Guillermo, in your case, in terms of separating the clay platelets from each other, you effectively need something to what is called exfoliate, right? And so, are you aware of what kind of materials are used for breaking up the platelets, separating them from layers? Okay. Okay. So now the question is, there are five different types of molecule functions. What to select in which case, right? So you can have binders, and these are some kinds of lubricants. So when you look at binders, there are a whole bunch of things people have used in trial and error in the past, like over the years, because the nature of working with powders has been dominated by either inorganic chemists, right? Whereas most additives are organic molecules, right? So in many cases, people are not familiar with the whole field, and so have to try out a lot of different things and then see what works. Otherwise, from a materials or a mechanical engineering perspective, in many cases, people just don't have their either ceramics background, because traditionally cements, bricks, and from there on clay, people were working with ceramic particles and so never really learned about polymers. Or they were metallurgists. Yes?
For example, we have a very high acidic solution.
Okay.
When we keep that solution in certain surface, that surface, what should be the property of that surface of that container which contains a acidic, very high acidic solution?
Okay. What kind of and what temperatures are you looking at?
For example, I am using 0 Celsius till 20 Celsius.
0 to 20. Yes. I think, I mean, and what's concentration of acid?
Uh, I have it's in sulfuric acid 95%, HF 1%.
Oh, you have HF. Okay, so that's the problem. I think either fluorinated polymer, like a Teflon or a modified Teflon, would be, I think, appropriate for something like that. And or high molecular weight polyethylene with a fluorinated surface.
Polyethylene I used the last time. The reactor was blasted. I don't know what happened with that, but
Okay,
I was worried because I need to make another one.
okay. You can try either a. There are fluorinated polymers, and we'll try to take a look at some variations. FEP is the name of the. It's a short form for the type of polymer, and you can buy that from a standard company, and that might be appropriate for what you're looking at. Okay. It brings a good point in terms of chemical compatibility. It's not just with the solid, but the chemical compatibility with the powder becomes an important attribute as well. Hi, come on in, Rafael. Yes, so in many cases, some powders are reactive. And when you deal with nanoparticles, they can be a lot more reactive than with coarser particles. And so the impact of the selection to not degrade the polymer or the solvent or not react with it is an important attribute in selecting the right material for the given system. Okay, temperature becomes an issue as well. There are some, in the case of processing with solvents, you're doing it at relatively lower temperatures, but if you're processing as a melt, you're doing it at a much higher temperature. So if you're combining three or four different additives, the boiling point of one of the additives, the degradation temperature for some of the additives, all that makes a difference in the selection. Okay. So here what you have earlier on, the different kinds of waxes are relatively lower molecular weight materials. Okay. They are solids at room temperature, but at relatively low temperature between 40 to 60 degrees centigrade, maybe sometimes closer to 80 or 90, many of them will completely melt. Okay. Then you go down to a lot of different thermoplastic materials over here. And so in that case, what you have to do deal with is materials that you can heat and cool, so cyclically without a problem. But then you have a number of thermosetting materials, okay, over here. So thermoplastic, thermosetting, we need to just get a refresher on what is the meaning of the terms and how we distinguish between them. And then finally over here you have several molecules that are naturally derived. And so they are carbohydrates, and so they can be obtained from plant or animal sources. Right? And then you have a number of smaller molecule materials and solvents and oils, okay, over here. They don't need to be all completely organic. They can be some salts, they can be some inorganic materials as well, and that can polymerize. And these are some things. When can we use them? When should we avoid them? Are important issues to pay attention to. In terms of lubricants, again, some of the things that you have to worry about is you're largely dealing with relatively smaller molecules compared to with binders. The main thing is you have this term, which is common to both of them, and they they relate it to a hydrocarbon chain, stearic. So hydrocarbon chain, carbon hydrogen, which is relatively lower molecular weight, typically about 16 to 18 carbon atoms, okay, in one of them. In this case, there are two of them, and in this case also there are two of them. And so the presence of the hydrocarbon, it's oily, it's waxy, and so that property on the one hand is able to reduce the friction. There's another part of the molecule, okay, in this case it's the zinc and the acid that is coordinated with that. In this case there are some nitrogen based compounds, and so they can interact with the surface of the powder and stick to the surface of the powder. So one part of the molecule sticks to the surface of the powder, the other part provides an oily coating to reduce wear between the friction between the two particles. So with that background as to the types of compounds that we are dealing with when we are trying to mix organic additives for various processing methods with powders, is we have to deal with issues related to selection of these different materials, right? Now, what do you know about a polymer? We know that you haven't had, Rafael, you had some course in polymer chemistry?
Yes, I had quite well. I had about two or three subjects about it.
Okay, great. How about you, Guillermo?
Me too.
Okay,
Good.
okay. So the rest of the class will balance these out, and then you can feel free to answer questions, and then we'll try to see with the rest of the class as well how they come along. Right? So, what are some attributes of polymers that make them different from small molecules? What are some characteristics?
The large chains,
Right.
it's something unique, but the entanglements between the large chains are something that usually has major effects.
Okay, so that is very good. So that's a good starting point. It is not just the molecular weight, but the fact that they are really long molecules that can then be connected to each other in different ways. They can be physical forces, and so they can just be tanglements. So you have a bowl of spaghetti that you cook, right? If it's a box of spaghetti, it just slides out before cooking, and they just move past each other very easily. But in a bowl of spaghetti, it's hard to separate the chains from each other. So there is a resistance to deformation. You apply a shear force, they do not, you have to provide a much higher force for the molecules to move past each other. Now you need to overcome those intermolecular forces to change the shape of the material, right? Now with water, you have just hydrogen bonding interactions, and so you can easily move the water molecules past each other. But the physical forces connecting the polymer chains, right, are much larger because there are many per molecule. And so for a molecule to separate past each other when it's very high in molecular weight, right, requires more deformation. And that is the principle behind injection molding, right? So the main thing is, in most of the cases, you have, if this is one monomer, one mer, right? If you have one of them, if you repeat it for a small amount compared to repeating the same thing for thousands or tens of thousands of times, you have very different properties. And basically, there is a certain threshold when the number of entanglements between the chains becomes significant. Okay. So the main thing is repeat units. Okay. And so based on that change in molecular weight, you can have a lot of different properties compared to metals or ceramics. The weight's much lower, so that could be a way to select them. They can have corrosion resistance. Again, depends upon the material. But for instance, with acids, as Sherdil was discussing, you can have some attributes that allow them to have some resistance related to that. But that again depends, because some polymers will dissolve in water, and so, or they will swell in water, and so they will deform, and so that becomes a big problem. They're going to be lower in strength and lower in stiffness compared to metals or ceramics. The main thing is the temperature in which you can create a shape is a lot lower compared to the temperature required to create a shape out of metal or ceramic. And so that is the advantage of first using the polymer to create the shape. And once you have the shape that you want, right, at relatively lower temperatures and forces, you can get rid of the polymer and now you can fuse the particles together. Right? So energy efficiency is higher when you're working with this particular format. Okay. Of course, polymers after a certain point are going to degrade. And so how high a temperature you can use them becomes a major issue. However, different polymers have different stabilities. We will see in the class day after tomorrow, when we are trying to burn out the polymer, we get to understand stability issues with temperature, right? How they break down and what residue they leave behind.